So in the last video, we talked about center of gravity, and in this video, we're going to discuss toppling instability. So toppling is interesting. You've probably, played around with it. How far can you incline something before it falls over? Okay, so I've drawn out 3 different scenarios. In the first scenario, right here, we have a block resting on an incline. We see the center of gravity is right in the middle of the block right here. It's at its geometric mean. And the center of gravity is within the base of this block. Okay, and basically to determine this line, it's just a vertical line straight down from the center of gravity point. All right, now in the second example right here, I have the same block resting along a incline that has a slightly larger angle, and the center of gravity is still right in the middle. And I see that this vertical line that goes straight down from the block is still, you see, within the base of the block. So remember, to support an object, all I have to do is support its center of gravity. Recall that in the meter stick example, if you can support its center of gravity, you support the entire meter stick. Okay. Now, in this third example, I've increased the incline even more. I have the same block. Here's the center of gravity. But I see when I draw this vertical line straight downwards, it falls outside the base of the block. Therefore, I am no longer supporting the center of gravity, and this block is actually going to topple straight down. So the rule for toppling is that if the center of gravity is supported by the base, then it will remain upright. Otherwise, it will topple. So we see in this last example, the center of gravity, this line, was not within the area of the base. Therefore, it toppled. Another interesting example to consider is that this base area actually doesn't have to be a solid. If we look at a table, so, you've got 4 legs. Okay, center of gravity is somewhere in the middle of this table, like right around here. Okay, so we see that, the center of gravity is actually in an area that doesn't contain table-like material, right? But it's within the base area. Here's the base area. So the 4 legs are able to support the table. If, let's say, I get rid of this third leg, so let's say that this first leg, so now I just have 3 legs. Okay, so now my base angle is a triangle, so something more like this. But also, your center of gravity will shift a bit because your mass has changed. It's slightly over here. So even without this third leg, my table will still remain upright because it is within this base area of support. So again, your general rule is an object will remain upright if the center of gravity is within its base of support. Another interesting thing to consider with center of gravity is that center of gravity will always want to be as low as it possibly can be. So you've probably seen these sort of toys where you've got like a really light body, and then a heavy base. Like this might be made out of something really heavy and the rest is filled with air. So its center of gravity is relatively low because of this very heavy base. Now, you've probably noticed that if you push this to the side, for example, it will almost automatically turn upright again. And that's because its center of gravity is lowest when the toy is upright than if it's pushed to the side or turned upside down. So, when an object is balanced in a way that displacement raises its center of gravity, then we say it's in stable equilibrium. For example, the way this toy is right now, this is the lowest point that its center of gravity can be, so this is in stable equilibrium, because if I turn the toy upside down or I move it in any way, its center of gravity is raised, and then it's unstable. So this is considered stable equilibrium. Now, the opposite of stable equilibrium is an unstable equilibrium, and that will happen when a displacement actually lowers the object's center of gravity. So unstable is essentially the opposite of stable equilibrium. And then there's one other scenario, neutral equilibrium, where the center of gravity is neither raised nor lowered by such movement. So here's a quick example to show you the differences between the two. So we see in this first example where the cone is on its base, this is in stable equilibrium because the center of gravity is as low as it can possibly be. Okay. In the second example, with unstable equilibrium, the cone is now inverted and is balancing on its tip. The center of gravity is higher in this case, so this is an unstable equilibrium. You probably tried to balance a cone maybe on your hand before with its tip as the base, and it's very difficult because this area here is very, very small, so it's very difficult to have the center of gravity be supported by this extremely small base. Okay, another interesting example to look at is if I have, say, 2 books. So let's just consider one final example. In this scenario, I have 3 pens. I have a pen lying on its side, a pen on its tip, and a pen balanced on its base. Okay, so we see that the pen lying on its side is in the most stable position because its center of gravity is as low as possible. Any movement would raise its center of gravity, and it would be in an unstable equilibrium. So this is great. Okay, now looking at this pen on its tip, we see that this is in an unstable equilibrium because any movement here would lower its center of gravity. We also see that it would be very hard to balance a pen like this because its base area is very small, and to line it up with its center of gravity would be very difficult. So looking at this last example, we have a pen on its base. And surprisingly, this pen is also in stable equilibrium. And that's because any movement done on this pen would actually raise its center of gravity because the pen has to roll over its corner. So it looks something like this. And its center of gravity would be slightly higher. Okay, and remember that something is in stable equilibrium if displacement raises its center of gravity. So in this case, displacement does raise its center of gravity, and the first scenario, this one right here, was in stable equilibrium, even though its center of gravity is higher than the pen center of gravity laying on its side. Also in this case, in this one, and in the last one, I would have to do work to raise its center of gravity, and that's not favorable. So this sort of wraps up our discussion on toppling and stability, and in the next video we'll start to talk about torque and angular momentum.